Hello everyone, January the 4th. Well, have you ever watched a video that just make you feel so much, make you feel so warm, make you feel so motivated, make you feel so nice? Yeah, I have a video like that. Well, I just watched it. It's Clarence Kennedy and Gabriel Sinclair and Max Out. Man, Gabriel just did 240 kilos front squat without warming up. I mean, you see that? That's just what an Olympian can do. I mean, he was bronze medalist in 2016. Yeah, they reached the pinnacle of the sport, and then that's what they do. They just simply dazzle you. All right, so one thing to note is I was a little bit taken aback at what this knapsack thing is for that problem, but then I thought about it. That is knapsack. That is exactly knapsack. And actually, this part is exactly knapsack. It's a knapsack problem, right? So knapsack problem is you have a bunch of stones, a bunch of stuff you want to fit on a knapsack to not exceed the total weight limit. And this is the same. We have a bunch of things. So if we sort it, so we have a bunch of things. What are the things called? Partitions are a bunch of numbers. And then we want to pick however many we want so that the total sum, like the total weight, is smaller than k. So it's exactly the same problem. It's exactly the same. So the way we think about that is for each stone, for each number, we can choose to take it or not take it, right? So if we take it, then we have to add this minus thing, right? We have to add this. Basically, for each one, we have to consider different weight, right? From the top all the way down. And then I just realized I can just go down to num's I, right? And then for each weight, if you take it, then you have to add dp this weight minus yourself because you want to take it, right? Or you can choose not take it. So if you not take it, you have to say, okay, if I'm not taking myself, then I have to take the weight, the limit of the weight without me, which is just dp lim. So this whole thing that I was trying to solve yesterday was, just rediscovering how knapsack is done. So I'm going to redo this again, redo this part. You know what? I'm actually reading it right now, right? So can I just say, yet another update. Update again. Use knapsack idea to do the DP part, right? So it's exactly the same, but this, we don't go down here. We go down to num's I, and we can't reach num's I because if we reach num's I, actually we can't reach num's I, right? -1. So this one is not needed. And then we'll say dp there equals plus dp lim. All right, so this part is not taking anything, right? This part is not taking anything. And this part, I don't know, this part is taking. This part is taking. So like taking, what did I just say? Take num's I or not take num's I. That's the knapsack. If I take num's I, we have to do limit minus num's I. If I don't take num's I, then for the current, it's just going to become this, right? Once we're done, we do the impossible, which is the last one, right? The last one. And it's just going to be 1 plus take num's I. See, this is take num's I or num0 or not take num0. So basically that's that. And it will be the same. But I'm not going to submit it because that's basically the end of the whole problem. So that's it. Figure it out. Yeah, I'm gonna keep this in my mind about how knapsack is done. Hopefully that I'll be able to remember knapsack. Yeah, it sounds familiar, right? That's fine. We'll relaunch it. That's okay. Oh, it remembers. All right, that was unexpected. All right, minimum number of arrows to burst balloons. I think I've done this before. Some spherical balloons taped onto a flat wall that represents the XY plane. The balloons are represented as a 2D integer array that denotes the balloon whose horizontal diameter stretches between start to end. Yeah, I remember this. You do not know the exact y coordinate of the balloons because it doesn't really matter. It's just a range. So there's another problem dealing with range. Range, and range. Arrows can be shot up directly, vertically, of course. They go up vertically. From different points along the x-axis. A balloon with x start and x end is burst by an arrow shot at x if it's yes. There is no limit to the number of arrows that can be shot. The shot arrow keeps traveling up infinitely, bursting any balloons in its path. Given an array point, return the minimum number of arrows that must be shot to burst all balloons. So we are trying to find the minimum numbers of overlap. Yeah, if a balloon has no overlap with the others, then you will have to shot it with one arrow. But if there's overlap, so we try to find as much overlap as possible. The first one, we have the range 10 to 16, and then 2 to 8. Okay, 2 to 8, and then 1 to 6. Oh my god, these are all not overlapping, and 7 to 12. So our overlap. Now 1 to 6 is no overlap, so this one has taken 1, and then we're overlapping 7, 12, and 10, 6. They overlap, but 10, 16, and 2, 8 is not overlap. So at least we need to take 2 shots. So add together is oh, 1, 2, 6 is overlapping. Jesus, come on, man. 1, 2, 6 is overlapping with 2, 8. Oh, I was completely wrong. 1 to 6, 2 to 8, 7 to 12, and 10 to 16. Okay, 1, 6 is overlapping 2, 8. So we need to take a shot. And 7, 12 overlapping 10 to 16. So we take a shot. That's 2. Okay, so now next one, we have 1, 2, 3, 4, 5, 6. So then none of them overlap. So you have to shoot 4 arrows. The last one, 1, 2, 2, 3, 3, 4, 4, 5. So we need to take 3. No, 2. Oh, come on, I always say 3. That's only 2 arrows. Okie dokie. I don't remember, but usually this type of problem, when we're trying to find overlap, we'll sort based on, say start. Okay, so sort based on start. We have 1, 6. Right, and then 2, 8. I'm looking at the first one. 2, 8, 7, 12, and 10, 16. Right. Now, each arrow must be shot with 1. Each balloon must be shot with 1. Right. So we try. If we try to do it, greedy, is we want to kill one balloon with as many overlaps as possible. So if we sort them and then we try to see how many of them are overlapping, Like if there are non-overlapping, we have to shoot one. Like the first one, we have to shoot. Right? We just want every arrow to be as maximum as possible. Right? So we can shoot that. Basically, we go through, we find all the overlap with the first one, then we eliminate them, and then we start a new one. Because if there's no overlap, you have to shoot it, right? And then we try to find overlap. I think it's just to find the overlaps, right? We just find the overlap. We sorted it, and then we try to find overlap with the starting one, right? With the starting one. So we record the start, end, and then we try to see how many front can we hit. I feel like that should be enough, because what other ways can you shoot the arrows? I mean, that's the best way to shoot them, because every balloon has to be shot. It doesn't really matter where you shoot it. Okay. No, 2023. No, 2022. Copy 2022. This is 2023. All right, that's that. All right, what do we have? We're gonna do points. Sorted it, as always. After sorting, what do? We are going to say res equals 0. And then we're going to I equals 0 for this, and then I equals j. Something like that. Let's see. While I is smaller than len points, okay? And then j equals I and equals points I 1 and j equals I plus 1. While j is smaller than len points and points j 0 is smaller or equal to and j plus equal 1. So the first one, j is outside, will come out, right? Will come out. Yeah, because we'll shoot the current one anyway. So res plus equal 1, I equal to j. Then I go back up, try it again, and then I'll return res at the end. All right, let's give this a shot. Points, find, looks good. You wanna test some? I'm too lazy. If it's not right, then it's not right. Ugh. It really is not right. Wow, I was able to solve it in the past. One shot. What was the problem? Something I did not take into consideration. What did I not take into consideration? Oh, output is 1, expected 2. What the hell? Oh, too fast, man, too fast. Three, 4, 6, 6, 8, 9. Oh, see. I see. Holy crap. I know. I know the problem. I can not only consider that. I have to also consider... Damn, I have to also consider the right. So yeah, the first is this, and then we did the next one, right? And then we have to shrink the right. We have to shrink the right. So next one's 3, 9. We have to shrink it. Now it's 9. The next one, 4, 11, has still 9. And then 6, 9, and still 9. 6, 7, that becomes 7. And then 8, 12 can do it. Oh, you're right. We want to go minus type 1. So we want the larger one go first. And then, oh boy, small equal to end. Then we say end shall equal to the minimum of end points J1. We keep the smaller one. Right, we keep the smaller one and then go back up. Go back up when they come out. So with this, I think I got it wrong. Need to be this. Now we pass. It was an oversight. You don't realize. This one should be right. Oh, that was so slow though. 4 seconds. Okay, something's not right. Sort by left ascending and if left is the same, sort by right descending. Then go then one by one find all the intervals that overlap. And each time we compare the new intervals left to the overall to the smallest right, yes, smallest right currently encountered, right? Once all the overlapping intervals are found, we're good, right? We record one arrow. This is ON, right? Because I visit everyone only once. I don't understand why it's so slow. The only thing I can say is maybe. So I don't have to take a look at this. I know what this is. Take a look at this. Oh, I do, because I want to know the number of test cases. 48. 49. We added one more test case, that's why. Oh my god. Oh. Hold up. Wow, that was very different. low and high. If next low is larger, else low and high equals next low. Huh. Interesting. Is that the same? Yeah, probably don't have to sort twice. Oh yeah, I don't have to sort twice. I didn't sort once. Uh, yeah, sort by the left is sufficient. And I can just keep going, right? A new left, if it's larger, then we record. Alright, otherwise, if the right is, otherwise we just keep recording the smallest the right. Actually, no, I want to do new solutions. No need to sort by both left and right. Sort by left is sufficient. Okay, let's see. Sort by left. What is it? Sort, and for I in range, one to len points. Wow, we don't need to write. 0, 1. Okay. And we can say if points I 0 is smaller or equal to, now if it's larger than, and rest plus equal 1, right? Rest plus equal 1, and equals points I1. Elif, so it's smaller, else and equals to minimum and points I1. Right, and then we go to the last one. Because we have to add this. So we have to do +1. Yep. This is good. This is much better. I'm not sure much better, but it's all right. All right, I saw that I called it ON. That was not right. I mean, we can say +n. Sort based on the end. That's actually interesting. Solution 3, sort based on the right. So, the smallest and the front. Oh, smallest and at the front. And then those will even be smaller at the left. So the next one, we can say, next. Well, I think we don't have to do the minimum, because if we sort based on end, it won't be the case where the two are overlap. Not overlap, they will, yeah, because we sort based on end. This is not happening. So the left can be, in and out, doesn't really matter. All that matters is the new left is smaller than the previous end, right? Because if I come here, the next one's guaranteed, so it's like here. Doesn't matter, right? If it's larger, what if it's smaller and this is larger? And then we can just shoot those, and then we can, because that one is, next one. Yeah, we can sort based on right. Then end is still this, right? Then again, if this is larger than end, I think we don't need this. We don't need to do this. I mean, we just need an end, so we can actually, we don't even need this. We can say end is equal to yeah, I guess that's fine. What was the solution say? Not this one. Minus math dot inf. Ah, yeah. Can do that. We can do that. Minus math dot inf. Oh, so you add a one on the front. Ah, that's all right. That is absolutely all right. All right. Okay. Count the digits that divide a number. Given an integer, return the number of digits in num that divide num. The number of digits, 7. 7 divides 1. Divide 1. Divide, so 1 divided by, yeah, 1 does. 2 does not. 1 does. 1 does. 2 does. 4 does. 8 does. Okay. That shall do, right? Oh, whatever 0 does not contain 0. Okay. It's good that you realize it could be 0. Good for you. Oh, there are easier ways to do this. How about I don't care? Fair enough. So you take a look. That's all right. Distinct prime factors of product of an array given an array of positive integers nums. Number of distinct prime factors in the product. A number greater than 1 is a prime. So just 2, 3, 7, and 5. Right? So basically we're trying to find the prime factors of every single one of them. And that's basically it. And it's only to 1000. So we only need to find prime from 1 to 500. No, 500. 1000 divided to 2. Yeah, 500. The 500, we'll find all of them. And then for each one, we basically just look for them. Right? I mean, what else can we do? What else can you do? We can actually even first do an in. So that's how I would do it. If we don't do it this way, then we have another way, which is just basically find all the prime factors for every single value. Yeah, but it feels silly to me. I want you to do this. Almost there. PF, I'm gonna do a set for any nums. For P in self.primes. Oh wait, I don't even need to. I just need to say 100 100. Just need to 1000 square root 31. 31. That's it. Yeah. Oh, actually, maybe it'll be easier than doing the, I don't know, math.sqrt p, not p, n. Alright, if p is larger than limit break, otherwise, if n mod p is equal to 0, pf.add p, and then blah blah blah, we return len pf. Yeah, you can figure it out without using the resource. What? First one ain't right. Oh, let's not do this. Oh yeah, let's do this, but hold up. If n in self.prime is only 31, pf.add p, add n, else, that's still not right. It could still be, yeah, you're right. So don't do this. Just go through the entire thing. Alright, just go through the entire thing. It's not a lot. It's not a lot. Just go through the whole thing. What? Oh, I think you're wrong. Oh, if we cannot have them, oh my god. Okay, so if this blah blah blah, oh, we have to. My bad. Is prime equals true. Okay, so if this, and then we say is prime is false, and then when we're done we say if is prime, if value is prime, then pf.add n. Yeah, I forgot. All right, absolutely correct. Jesus, a lot of values. I only add 11 now there. We have to do those 11, and then if none of those 11 can divide, that means this value itself is a prime, then we shall be able to add it. All right, just like that. That was a little bit oversight. I was going to say it's an oversight. I went wrong again. What? This is bonkers. Output 160, expecting 166. What am I missing? $166. Oh, shoot. Oh. If n is equal to p. No. Wait, no, it's fine. It is fine. Because I don't understand. Oh, now I understand. I want to find all uniques. Got it. So we'll divide, right? So we'll divide by this. If none of them divides, then that is that is a prime. If somebody divides and the result, the result. But how do you know if the result is a prime? Right? How do you know the result is a prime? It's a good question, right? It's a good question. How do you know the result is a prime? You don't. You don't know. Like, seriously, you don't know. Right? You don't know. So you go through all of them. Then you have to check. Yeah. You do have to check. And how do we check on this? Exactly, how do we check? Maybe we have to... I don't know. It looks like we do have to add everything. All the way to 500. That looks silly, huh? Well, we can do early stop. That's okay. That's okay, we can do early stop. Actually, we might need to even more. So what if I have like 709, 701? Well, for that, or let's say, oh yeah, let's do 500. It's the smallest is, yeah, like if it's bigger, then we can also always divide, so it becomes smaller, right? Or if it's not, then we go through everything, then it's just, yeah, I think 500 is sufficient. Wow, this one's harder than I had expected. Right, and then we go through all of them. right? We will store all of them, and then if P is larger than, and then we'll break. Yeah. I don't like it now. I don't like it at all. I don't like it. Yeah, I don't like this. Have to obtain list of primes smaller than 500. I thought I don't need to do that, but then the issue arises when when a number is multiple of say 2 times, you know, 2 times 401, right? If I have to include all the primes below 500 to handle this situation. Call it ON. Every time ONM. I don't know. What are the other? I mean, we can just keep going, which I guess maybe it will be right as well. Let's try. Let's try. Obviously, we don't like this one. So this one I don't have to do this. Just naively try all the naively finding all the prime factors. Okay, so I'm gonna do a def prime factors. Count. No, I can't count unique prime factors. I need to find prime factors, unique, distinct prime factors. So give it n. Pf equal to a set, and then we say while n 2 equal to 0. Like this. If n equal to 0, pf dot add 2. And while n right, and then we say p equals 3. Actually, while n p equal to 3, if n p f now p defined on the outside. So either 0 pf.add p while p and done p plus equal to 2 all the way until that, and then we return pf. Okay, and then this for n in nums, pf set pf dot union self dot distinct and let's see. What the hell is wrong? Oh, while n. No. Larger 1. Still no. Why do I do pf equal to? Yeah, pf equal to. Okay. Maybe this is the preferred solution. Try this. Maybe. Should have gone with this route to begin with. Like, to be honest. Not really. Not really. I mean, maybe they're duplicates? I don't know. I honestly don't know. Or we can build up. Yeah, maybe we can build up. We don't have to do this everything from scratch. What do people say? Large prime optimization. Oh yeah, that's the thing. You only need this. Oh, you keep removing. Oh, I see. Large primes. Because I only divided once. That's why I can't be sure. Yeah. I see the point. Combine basically is a combination of my two methods. That's what it is. Do go all the way to 31 because that's sufficient. We just have to, keep going through, right? Keep taking away prime factors. Okay. The last one standing must also be a prime. That's how we resolve big prime problem. Given number contains big prime factor. So we don't have to do this. basically what we're gonna do is just reduce, right? What do? We say distinct prime factors. For P in self.primes, if n mod P equal to 0, pf.add P, and then while n larger than 1 and mod P divided equal to n divided equal to P. Right? Blah 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 blah. Once we're done, go back up. If P is larger than n, then we can break. Right? And then if n is not equal to 1, pf.add P. Not add n. This is handle large prime factor. Oh, now it's much easier. Yep. That's more like it. Okay. All right, that'll be it. Yeah, not my best day. All right, I will see you guys